Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are tackling OSPF LSA types and area types, which is one of the most commonly examined topics in CCNA, CCNP, and CCIE. OSPF does not simply flood a single type of routing information across the entire network. Instead, it uses several distinct LSA types, each with a specific scope and purpose, and it restricts which LSA types can enter certain area types. Understanding both what each LSA carries and where it is allowed to travel is essential for designing and troubleshooting OSPF networks. By the end of this series, you will have a mnemonic for the 6 LSA types used in practice, and a clear mental model for every area type that tells you instantly which LSAs are present and which are blocked. LSA Types 1 and 2 Router and Network. LSA Type 1 is the router LSA. Every OSPF router generates exactly one Type 1 LSA describing all of its directly connected links, their states, and their costs. The Type 1 LSA is flooded only within the area in which it originates. It never crosses an area boundary, which is why routers in different areas do not know the detailed topology of each other's areas. They only know the summary information that an ABR derives from those Type 1 LSAs. LSA Type 2 is the network LSA. It is generated only on multi-access networks such as Ethernet segments where a designated router has been elected. The DR generates a single Type 2 LSA on behalf of the entire broadcast segment, listing all routers attached to that segment. Like the Type 1 LSA, the Type 2 LSA is flooded only within its originating area and never crosses an area boundary. On point-to-point links there is no DR election and therefore no Type 2 LSA is generated. Because Type 1 and Type 2 LSAs describe the internal topology, they are present in every area type without exception. There is no OSPF area design where Type 1 and Type 2 are blocked, because without them routers within the area could not build the local SPF tree needed for intra-area routing. LSA Types 5 and 7 External and NSSA External. LSA Type 5 is the AS External LSA. It is generated by the ASBR and flooded throughout the entire OSPF domain, with the exception of stub areas and NSSA areas, which explicitly block it. Each Type 5 LSA describes a single external prefix, its metric, and the metric type. Type E1 external routes add the internal OSPF cost to reach the ASBR to the external metric, so the cost grows as the route propagates. Type E2 external routes preserve only the external metric regardless of how far the ASBR is, which is the default behavior when redistributing into OSPF. LSA Type 7 is the NSSA External LSA. It exists specifically to solve a problem. Stub areas block Type 5 LSAs, but some stub areas have their own ASBR that needs to import external routes. NSSA was created to allow this. When an ASBR is inside an NSSA, it generates Type 7 LSAs instead of Type 5 LSAs. Type 7 LSAs are flooded only within the NSSA. When they reach the ABR connecting the NSSA to the backbone, the ABR converts each Type 7 LSA into a Type 5 LSA and floods it into the rest of the OSPF domain. This conversion is called Type 7 to Type 5 translation. The distinction between Type 5 and Type 7 is purely one of scope and area type. Both describe external prefixes. The difference is that Type 7 travels only inside an NSSA while Type 5 travels everywhere else. In a totally NSSA, even Type 3 LSAs are blocked, and the ABR injects a single Type 3 default route to cover all inter-area and external destinations. Backbone and standard areas. All 5 thrive. The backbone area, Area 0, and any standard non-backbone area except all 5 core LSA types without restriction. Type 1 router LSAs describe the internal topology of routers within the area. Type 2 network LSAs describe multi-access segments with ADR. Type 3 summary LSAs bring in inter-area reachability from other areas through ABRs. Type 4 ASBR summary LSAs identify the location of any ASBR in the OSPF domain. And Type 5 external LSAs carry the actual external prefixes redistributed by that ASBR. The memory hook for backbone and standard areas is all 5 thrive. All 5 LSA types are present and active. There are no restrictions, no filters, no blocking. Any router in a standard area has full visibility into inter-area routes and external routes through the complete set of LSA types. It is important to note that Type 1 and Type 2 LSAs are always area local. Even in a backbone area, a Type 1 LSA generated inside Area 0 does not travel into Area 1. The ABR converts the topology information into Type 3 summary LSAs when crossing area boundaries. What all 5 thrive means is that all 5 types can exist within a standard area, not that all types cross all boundaries freely. Totally stubby area 2's the limit. A totally stubby area is a Cisco proprietary extension of the stub area concept. It goes one step further by also blocking Type 3 summary LSAs in addition to Type 4 and Type 5. The only LSA types present inside a totally stubby area are Type 1 and Type 2, which are the area local topology LSAs that cannot be blocked without breaking OSPF entirely. Everything else is filtered out by the ABR. With Type 3 LSAs also blocked, routers inside a totally stubby area have no knowledge of any other OSPF area's subnets. Their routing table is extremely lean. The ABR injects one single Type 3 LSA representing the default route quad 0/0, and routers use that for everything outside their local area, whether the destination is in another OSPF area or an external network entirely. This produces the smallest possible LSDB and routing table, which is ideal for remote branch offices with a single uplink. The memory hook for totally stubby areas is 2's the limit. Only Type 1 and Type 2 survive inside the area. The number 2 is the limit. Only the ABR needs to be configured with the no summary keyword in addition to the stub configuration. Internal routers only need the stub area configuration and will automatically receive only Type 1, Type 2, and the single default Type 3 from the ABR. This is a Cisco proprietary feature, so other vendors may implement it differently or not at all. NSSA and totally NSSA, normal +7, and 2 and 7. The NSSA, or not so stubby area, was created to solve a specific problem. What happens when a stub area needs its own ASBR? A pure stub area would block the external LSAs that ASBR needs to advertise. NSSA resolves this by allowing external routes to enter through a special Type 7 LSA instead of a Type 5. Type 4 and Type 5 LSAs are still blocked at the ABR, but Type 7 is allowed to exist and flow within the NSSA. The ABR then translates Type 7 into Type 5 when forwarding the external routes toward the backbone, making them visible to the rest of the OSPF domain as standard external routes. The LSAs present in an NSSA are Type 1, Type 2, Type 3, and Type 7. The memory hook for NSSA is normal +7. It behaves like a normal stub area with Types 1, 2, and 3, but adds Type 7 as the mechanism for importing external routes. The word normal represents the stub baseline of Types 1, 2, and 3, and 7 represents the NSSA specific addition. The totally NSSA combines the totally stubby restriction with the NSSA external capability. It blocks Type 3, Type 4, and Type 5 just like a totally stubby area, but it allows Type 7 for external route import within the area. The LSA types present are Type 1, Type 2, and Type 7 only. The ABR injects a default route as a Type 3 LSA for all other destinations. The memory hook for totally NSSA is 2 and 7. Types 1 and 2 for local topology, plus Type 7 for local external import. That is the complete set. Type 1 LSA. Router LSA Deep Dive. The Type 1 Router LSA is the foundational building block of OSPF's linked state database. Every router in an OSPF area generates exactly one Type 1 LSA and floods it to all other routers within the same area. This LSA describes the router itself, its router ID, all of its active OSPF-enabled interfaces, and the state and cost of each link. The Type 1 LSA contains 4 types of link descriptions. A stub link describes a network with no other OSPF routers attached, such as a loopback interface or a LAN with only one OSPF router. A transit link describes a connection to a multi-access network with ADR, such as an Ethernet broadcast segment. A point-to-point link describes a direct connection to another router with no DR required. And a virtual link describes a logically constructed link used to connect discontiguous areas through a transit area. When OSPF runs the Dijkstra SPF algorithm, it uses the combined Type 1 LSAs from all routers in the area to build the complete topology graph. Each router then computes the shortest path tree from itself as the route to every other destination within the area. The accuracy and freshness of Type 1 LSAs is therefore critical to correct routing. When a link changes state, the affected router generates a new Type 1 LSA with an incremented sequence number and floods it throughout the area within seconds. Type 3 LSA, Summary LSA and Route Summarization. The Type 3 Summary LSA is the mechanism through which inter-area routing works in Open Shortest Path First. When an ABR has a Type 1 LSA in its LSDB for a prefix in one area, it creates a Type 3 LSA describing that prefix and floods it into the adjacent area. Other routers receiving the Type 3 LSA treat it as a distance vector entry. They know the prefix exists and the cost to reach it via the ABR, but they do not see the detailed topology of the remote area. This is why Open Shortest Path First is described as a two-level hierarchy. Full topology within an area, distance vector between areas. ABRs can also perform route summarization on Type 3 LSAs. Using the area range command on a Cisco router, an ABR can aggregate multiple specific prefixes from one area into a single summarized Type 3 LSA advertised into the backbone. For example, 10 prefixes in the range 10.1.0.0/24 through 10.1.9.0/24 could be summarized into a single 10.1.0.0/20 Type 3 LSA. This reduces the LSDB size in other areas and also provides stability. If one specific prefix flaps, the summary does not change and no LSA update propagates to other areas. It is important to understand that summarization in Open Shortest Path First is only possible at area border routers for inter-area routes, and at autonomous system boundary routers for external routes. Summarization cannot be performed on intra-area routes. This is a deliberate design choice that prevents the SPF topology from becoming inconsistent. Type 7 LSA Translation and Translator Election. The Type 7 NSSA external LSA carries the same information as a Type 5 LSA, an external prefix, a metric, and a metric type of either N1 or N2, which are the NSSA equivalents of E1 and E2. N2 is the default. The key difference is that Type 7 LSAs are only flooded within the NSSA and are never propagated beyond the area boundary. When the Type 7 LSA reaches an ABR, the ABR converts it into a Type 5 LSA and floods it into the backbone, making the external route visible to the rest of the OSPF domain. When an NSSA has multiple ABRs, a translator election must occur to decide which ABR performs the Type 7 to Type 5 translation. Without this election, multiple ABRs might all translate the same Type 7 LSA, producing duplicate Type 5 LSAs in the backbone. OSPF uses a simple rule. Among all ABRs connected to the NSSA, the one with the highest router ID becomes the elected translator. This is the default behavior. An operator can override this by configuring a specific ABR with the NSSA translate type 7 suppress FA command to force that ABR to always perform translation regardless of router ID comparison. The forwarding address field inside the type 7 LSA is also worth noting. When the ASBR's next hop for the redistributed route is reachable within the NSSA, the forwarding address in the type 7 LSA is set to that next hop address. When the ABR translates the type 7 to a type 5, it carries the forwarding address into the type 5 LSA, allowing routers in other areas to potentially route directly toward the original next hop rather than always going through the ABR. If the forwarding address is quad 0/0, traffic is always sent to the ABR first. Configuring NSSA and totally NSSA areas. Configuring an NSSA uses the area NSSA command, applied consistently on all routers within the area including the ABR. Just as with stub areas, OSPF will not form adjacencies between NSSA configured and non-NSSA configured routers on the same segment, because the NSSA capability is signaled in the Hello Packet Options field. When an ASBR inside the NSSA redistributes external routes, it automatically generates Type 7 LSAs instead of Type 5 LSAs. No additional configuration is needed on the ASBR beyond the standard redistribute command. The OSPF process detects that the ASBR is inside an NSSA and switches to Type 7 automatically. The ABR connecting the NSSA to the backbone detects incoming Type 7 LSAs and translates them to Type 5 LSAs, flooding them into Area 0 and beyond. By default, an NSSA ABR does not automatically inject a default route into the NSSA the way a stub ABR does. If you want the NSSA routers to have a default route for external destinations not covered by local Type 7 LSAs, you must explicitly add the default information originate option to the area NSSA command. Converting an NSSA into a totally NSSA follows the same pattern as totally stubby. Add the no summary keyword only on the ABR. The ABR then blocks Type 3 summaries and automatically injects a Type 3 default route, giving routers a single exit path for all destinations outside the area. LSA aging and flooding mechanics. Every LSA in the OSPF LSDB has a maximum age of 3,600 seconds, which is 1 hour. OSPF routers refresh their own LSAs every 30 minutes by default, which is called the LS refresh time. When a router refreshes an LSA, it increments the sequence number and resets the age to 0 before reflooding it. This ensures LSAs never expire under normal operating conditions. When an LSA is received from a neighbor, the receiving router increments the age field by the INF trans delay value, which defaults to 1 second, to account for transmission time. The LSA then ages in the LSDB at 1 second per second. If an LSA reaches the max age of 3600 seconds without being refreshed, OSPF treats it as stale and removes it from the database. The router also reflood the max age LSA to notify neighbors that they should remove it too. This purge mechanism ensures that LSAs from routers that have left the LAN cleanly disappear from all LSDBs within 1 hour even if no explicit withdrawal is sent. OSPF also uses a minute LS interval of 5 seconds between consecutive originations of the same LSA from the same router. This prevents a rapidly flapping link from causing an LSA storm that would overwhelm the network with flooding. If a link flaps faster than every 5 seconds, OSPF will not generate a new LSA for each state change. Instead, it waits until the min-LS interval has passed and then generates a single LSA reflecting the current state. This rate-limiting behavior is essential for stability in large networks. Area Design Decision Guide. Choosing the right OSPF area type is a design decision that depends on 3 factors: the number of exit points from the area, whether the area needs to import external routes, and how aggressively you want to reduce LSDB size on internal routers. Understanding these factors and mapping them to area types is the skill that separates engineers who configure OSPF correctly from those who configure it optimally. Use a standard area when the area needs full routing visibility, has multiple exit points requiring intelligent path selection, or contains routers that need to reach specific external destinations through different paths. Use a stub area when the area has a single exit point or multiple exit points that are all equivalent, and external routes can be replaced by a default route without impacting traffic. Use a totally stubby area when even inter-area summaries are unnecessary because all non-local traffic exits through the ABR regardless, and you want to maximize LSDB reduction on internal routers. This is the most common choice for branch office areas in enterprise designs. Use an NSSA when the area is functionally stub-like but contains its own ASBR that needs to redistribute external routes, such as a branch office that also connects to a partner network or a legacy routing domain. Use a totally NSSA when the area contains a local ASBR but you also want to suppress inter-area summaries for maximum LSDB reduction. The totally NSSA is the most restrictive area type available and produces the leanest possible routing tables on internal routers while still allowing local external route import through Type 7 LSAs. Thank you for your attendance. Please consider subscribing to the channel and liking this video.